Hi, in this video I'm going to talk about linear regression and how we derive the equations we'll need for the algorithms. You should have already looked a bit in the IPython notebook and realized that there are two different implementations. The first one uses a formula to compute the weights it uses. The second implementation uses an algorithm called gradient descent. There's a very important difference between these two algorithms, and I'll talk a bit more abstractly about this than the actual derivations. I'll give you the ideas of how to get through these derivations, and then I'll talk about the differences between the two, and I'll try to look at what we do in the derivations as a general approach we'll apply several times throughout this machine learning videos. So just to remind you, we have data of the form x1, y1 through x capital N, y capital N. So then we define the error measure for linear regression to be the sum of I is 1 to n. So we sum over all the data points, x, y, 1, x2, y2, all the way through x and capital N. And then we consider our hypothesis given the ith data point. So this is what our hypothesis would predict in the ith data point, and we'll subtract the correct answer, yi, and then we'll square this thing. So this is kind of like 1 over n times this would be our in-sample error rate for some hypothesis h. So you could imagine in the simple case where we had data like this, that the hypothesis like this, call it h1, the error of this would be the differences of all the points to the line squared. So a feature of this model is that if you have a point far away, then this error would be very large because you square the distance. So you can actually think of it as drawing squares here. So all these would be very small squares and they wouldn't add up to that much. But this one guy that's far away would have a very big square. So this error would of this one point would be very large compared to the other points. Great. So let's then look into how we get equations for finding w's. So let me just remind you that the hypothesis that we consider, then h of x is w transpose x. So h is given exactly by a weight vector w. So we could write this instead as w transpose xi. So the question is, how do we find a good w? How do we find a good w? So this is the question. So the thing is, before actually going into this, I just want to show you an example. So maybe let's say that I have a function f of x. So this is like kind of a complicated function. Let me just give you a simpler function. This will be x squared plus 1. So you'll probably remember that this function looks like this. So how could I find the value that minimizes this? This is basically what I want. I have a function up here and I want to minimize this. I want to find the w that minimizes this. This is kind of similar to finding the x that minimizes this function. So I could just look at the plot and see that, oh, probably x0 will give me 1 and this will be the smallest value. But that's this general approach where I try to differentiate the function. So then I get x is 2x, the derivative of 2x, and then I set this equation equals to 0 and solve for x. And then I get x should be 0. Solves this equation, right? So then I get that the minimum is indeed, as I said before, in here at x is 0. So the way this works is because my function is convex and there's only one minima, and in this minima the gradient will be equal to 0, right? So I mean this would be the gradient at this point would be 0. So up here the gradient would be larger, and here it would be, but at the minimum it would be 0. So this is kind of a way of minimizing f of x. So I did this, in this case I could actually compute it directly. If I couldn't have computed it directly, I could have used this gradient descent idea where I might have taken a random point, like this point, then I could have computed the gradient at this point. So let's say this is 1. So I could have computed the gradient, maybe I should say this is a half. Then I could have computed the derivative in this point. So f of a half would be, well, this is 2 times a half, right? This is 1. And then I could have taken a step in the negative gradient. So this would be, so I'm at a half, then I would have taken a step in the negative gradient. So this would be over here. And, well, then I'm in minus a half. And then I could have computed the gradient in this point. This would be minus a half. This would have been minus 2 times a half, which would be minus 1. And then I could have taken a negative step, and then I would actually get back to the same point. So if I had maybe, so now I kind of used that my step size was 1. If my step size was lower, I would have jumped back and forth and gotten closer and closer to the minima. So this is the difference between gradient descent, where I kind of follow the gradient along instead of getting the exact solution. So this is a general approach, a very general approach. We have something we want to minimize, we'll compute the gradients and then use gradient descent. In some cases, as with linear regression, we'll be able to do the exact computations and actually find the optimal solution. So I'll just briefly sketch the ideas of how we compute the gradient of the in-sample error rate and how we actually solve the gradient equal to 0. So this is the error function we consider. The first idea is to represent the data in this matrix notation, and we'll be able to write the in-sample error in this linear algebra matrix vector condensed form. So we'll be able to write the in-sample error rate as this by defining this matrix and this vector. So to realize this, you should make sure that you really understand this equality, and then you should be able to see that if you take the squared norm of this guy and have 1 over n, you'll get the same as this guy over here. So then we got a new way of writing our in-sample error rate. You should then be able to expand this, and notice that it'll give this thing if we expand it and rearrange by realizing that these two terms are the same. And then we'll be able to differentiate this, and you should be able to see that this would be 0, and then this w will disappear, and this w will give us a 2 in front. And then we can take the 2 out and we'll get this equation. So this will be the gradient. So now this is what we could use for gradient descent. Stepping back and forth here. Then if we solve this equation for equal to 0, we will get this final equation. So this is the kind of abstract walkthrough of deriving these equations.